This here is another encryption problem, again related to the RSA scheme. Let's understand the question first. The letters in the English alphabet are represented with the first 26 natural numbers. So we map A, the letter A to number 0, B to number 1, C to 2, up to Z to 25. So this is essentially base 26 representation. So for instance, if you have a word like this, hello, we treat each of these symbols here as a number, and H, since it's the 8th letter, it maps to number 7. E is the 5th letter, so it maps to 4. L is the 12th letter, so it maps to 11, and O maps to 14. So essentially, this is, as I said, base 26 arithmetic, but the representation is, as you can see here. So A maps to 0. This is the number equivalent, and B to 1, C to 2, up to Z to 25. But C, since we do not want to use digits like 11 or 14 because they represent two characters, we don't want two characters to represent one single digit. So we just use letters A, B, C, etc. beyond 9. So these are the digits from 0 up to P. These are the 26 digits of 26 base 26 arithmetic. So this is what we are going to use. Therefore, for instance, the word hello actually means this representation 7, 4, 11, 11, 14, and it's in decimal, it becomes this number. So I can show you that this indeed is equal to the same number. So let me just convert this number to base 26. Okay, so it produces 74BBE, 74BBE. So 74 is 74, and B is 11, and E is 14, as expected, because so 7, 4, 11, 11, 14. So now the word hello is represented by the decimal value given here. So this is just the representation we use for the purposes of this question. Now, coming to the RSA scheme, we are given the public key here. And this is the number n. If you recall, n is the product of two prime numbers, usually denoted P and Q. And E is the exponent value. And to compute the code word, we just raise the message value here in this question. This is the message. We will raise this value to the exponent E and take modulo n. So obviously this is not a task you would want to do using pen and paper, and therefore I'm going to put this over here, and over here I'm going to open Wolfram Alpha, and I'm just going to write here, take my message, raise this to the exponent value here, and take modulo n. So this is the n value. And when you compute this, this is the result. Okay, so this is the encrypted message, or rather the code word corresponding to the word hello under this scheme. So this is the answer to part A. And one remark I would make here is, since we are working with large numbers, well, obviously you don't have to use Wolfram Alpha. You can use some other tools or some other programming languages if you like. For instance, Python is an alternative that I know produces the correct values for this. But for instance, I tried this on MATLAB. And if you don't do anything special, MATLAB cannot handle these large numbers. So in order to use MATLAB, for instance, you need to be careful. You need to use some special tools to use these quite large values at these computations. So be aware of the limitations of the platform you are using or the tool you are using so that you don't end up with incorrect results. So coming back to part B. In part B, I need to find the message for the code word given here. So this is the code word, and this is the encrypted value. And this is produced using this public key. And I want to decode this. Now, in reality, I shouldn't be able to do this because obviously using encryption, you don't want your code word to be decoded. So my purpose with this question is that you should select the public key very carefully, and a seemingly large number like this one may not be a very good public key value. So I'm going to demonstrate this, that the value in this question is not really a useful public key. We'll just factor this number because, well, you see instantly I get the result. These are the two prime numbers, right? Two distinct prime factors, and Wolfram Alpha was able to find it like under a second. So obviously this is a useless public key. Therefore, in reality, you should be very careful selecting your public keys, because now that I know the P and Q values, it's very easy for me to decode this word because I know what to do. First of all, let me keep this. So let me open a new tab here. I need the value P minus 1 times Q minus 1. Okay, so maybe I can copy this, paste here. Okay, so this minus 1 times this minus 1. So what I need to do is to find the multiplicative inverse of the exponent value E, which is given here, under modulo this value. Okay, so let me just also copy this. Here, solve D times E, which is this number, equals 1 under modulo this number. Okay, now I have this. I can decode this code word and remember how to do that. Let me just copy this number. So this is the D value. I'm going to raise the code word to this value. So the code word here to the power D modulo N. Modulo N is given here and is this value. Okay, this is the result. This is my original message. Let me copy this. Now, the only thing that remains is to find the word, that the actual message. So I'm going to convert this value into base 26. Okay, so this is my value in base 26. So I need to find the equivalent of this as a word. So M, this is the first digit. M corresponds to, as a digit, corresponds to W. And then I have 4. 4 is E. Then I have BB. B corresponds to L. So I have WELL. So let me put the message here, WELL. And then I have 3. 3 corresponds to D. Let me put D here. And then I have E. E is here. That corresponds to O. And then I have D. D is N. And finally, I have 4. And 4 corresponds to E. And therefore, the message is well done.